Evolutionary game theory is the application of game theory to evolving populations of life forms in biology. EGT is useful in this context by defining a framework of contests, strategies, and analytics into which Darwinian competition can be modeled. EGT originated in 1973 with John Maynard Smith and George R. Price's formalization of the way in which such contests can be analyzed as strategies, and the mathematical criteria that can be used to predict the resulting prevalence of such competing strategies. Evolutionary game theory differs from classical game theory by focusing more on the dynamics of strategy change as influenced not solely by the quality of the various competing strategies, but by the effect of the frequency with which those various competing strategies are found in the population. Evolutionary game theory has proven itself to be invaluable in helping to explain many complex and challenging aspects of biology. It has been particularly helpful in establishing the basis of altruistic behaviors within the context of Darwinian process. Despite its origin and original purpose, evolutionary game theory has become of increasing interest to economists, sociologists, anthropologists, and philosophers. The problem, an ounce of algebra is worth a ton of verbal argument, JBS. Haldane. The need for evolutionary game theory in biology started with a problem. The problem was how to explain ritualized animal behavior in a conflict situation. Why are animals so gentlemanly or ladylike in contests for resources? This was a problem that leading ethologists Nico Tinbergen and Konrad Lorenz were trying to address. Tinbergen proposed that such behavior exists for the benefit of the species. Maynard Smith couldn't see how this reasoning matched with Darwinian thought as he understood it, where selection occurs at an individual level and therefore defections to self-interest are rewarded while seeking the common good is not. Maynard Smith, a former engineer and highly competent mathematician, turned to game theory to answer the question. The suggestion that game theory might solve the problem was made by George Price, even though some unsuccessfully applied efforts by Richard Lewontin at using game theory had failed. Maynard Smith's way of applying these mathematics proved to be a far more realistic model, and came to be a major mathematical contribution in the field of theoretical biology. Classical game theory. Game theory was conceived by John von Neumann to mathematically determine optimal strategies in situations in which a competition between adversaries is taking place. A contest involves a number of players, all of whom have a choice of moves for the game. Games can be a single round or repetitive. The approach a player has in making his or her moves constitutes the player's strategy. Rules govern the outcome for the set of moves taken by the players, and outcomes produce payoffs for the various players. Rules and resulting payoffs can be expressed as decision trees or in a payoff matrix. Classical game theory essentially requires that all of the players make rational choices. As a consequence, it is fundamental in game theory that each player must consider the strategic analysis that the player's opponents are making in determining that his or her own strategic choice is appropriate. Adapting game theory to evolutionary games. On reflection, Maynard Smith realized that an evolutionary version of game theory does not really require that players act rationally, only that they have a strategy. The results of the game will test how good that strategy is. That is what evolution does. It tests alternative strategies for the ability to survive and reproduce. In biology, strategies are genetically inherited traits that control an individual's action, and strategies are algorithmic, just like computer programs. The key point in the evolutionary game theory model is that the success of a strategy is not just determined by how good the strategy is in itself. It is a question of how good the strategy is in the presence of other alternative strategies, and of the frequency that other strategies are employed within a competing population. It is also a question of how good a strategy plays against itself. Because in the biological world a successful strategy will eventually dominate a population, and competing individuals in it end up facing identical strategies to their own. Participants in the evolutionary game aim to become more fit than competitors, to produce as many replicas of oneself as one can, and the payoff is in units of fitness. It is always a multiplayer game with a very large population of competitors. Rules describe the contest as in classical game theory, but for evolutionary games rules include the element of replicator dynamics. In other words, the general rules say exactly how the fitter players will spawn more replicas of themselves into the population, and how the less fit will be culled out of the player population. The replicator dynamics in essence models the heredity mechanism, but for simplicity leaves out mutation. Similarly, evolutionary game theory only uses asexual reproduction for the sake of simplicity. Games are run repetitively with no terminating conditions. The results that are studied include the dynamics of changes in the population, the success, survival of strategies, and any equilibrium states reached. Unlike in classical game theory, players do not choose their strategy or have the ability to change it. They are born with that strategy, and their offspring will inherit that same identical strategy. Models. It is important to realize that EGT is not just a specialist mathematical treatment of animal contests to determine the dynamics and results, but in a manner similar to the field of evolutionary algorithms. It is a comprehensive model that encompasses the Darwinian process itself, including the central tenets of competition, natural selection, and heredity, all within the overall model. Therefore, it is a major vehicle to help understand and explain some of the most fundamental questions in biology, including the issue of group selection, sexual selection, altruism, parental curve, coevolution, and ecological dynamics. Much of the progress in developing understanding in these diverse areas has been aided by evolutionary game theory modeling, and many of the counter-intuitive situations in these areas have been explained and put on a firm mathematical footing by the use of these models. The common methodology to study the evolutionary dynamics in games is through replicator equations. These replicator equations in the context of evolutionary biology show the growth rate of the proportion of organisms using a certain strategy, and that rate is equal to the difference between the average payoff of that strategy and the average payoff of the population as a whole. Continuous replicator equations assume infinite populations, continuous time, complete mixing, and that strategies breed true. The attractors of the equations are equivalent with evolutionarily stable states. A strategy which can survive all mutant strategies is considered evolutionary stable. In the context of animal behavior, this usually means such strategies are programmed and heavily influenced by genetics, thus making any player or organism's strategy determined by these biological factors. Games. In game theory, various games are mathematical objects of different character, in rules, relative payoffs, and attendant mathematical behaviors. Each game represents different situations, in the kinds of problems that organisms have to deal with, and the possible strategies that they might adopt if they are to successfully survive and reproduce. To achieve a better feel for the challenges of these different situations, evolutionary games are often given rather colorful names and cover stories, which quite effectively describe the general situation in which the particular game places its players. It all helps develop a feel for the mathematics of the game and the problems the players face. Some representative games of evolutionary game theory are Hawk-Dove, War of Attrition, Stag Hunt, Producer Scrounger, Tragedy of the Commons, and Prisoner's Dilemma. Some of the various strategies that apply in these games are Hawk, Dove, Bourgeois, Prober, Defector, Assessor, and Retaliator. Depending on the particular game, the various strategies vie against one another under the particular game rules, and the mathematics of the evolutionary game theory are used to determine the results and behaviors. Hawk-Dove. The most classic game is the hawk-dove game. The game was conceived to analyze the animal contest problem highlighted by Lorenz and Tinbergen. It is a contest over a non-shareable resource. The contestants can be either a hawk or a dove. These are not two separate species of bird, they are two subtypes of one species with two different types of strategy. The term hawk-dove was coined by Maynard Smith because he did his work during the Vietnam War when political views fell into one of these two camps. The strategy of the hawk is to first display aggression, then escalate into a fight until he either wins or is injured. The strategy of the dove is to first display aggression, but if faced with major escalation by an opponent, to run for safety. If not faced with this level of escalation, the dove will attempt to share the resource. Given that the resource is given the value V, the damage from losing a fight is given cost C. If a hawk meets a dove, he gets the full resource V to himself. If a hawk meets a hawk, half the time he wins, half the time he loses, so his average outcome is then V2 minus C2. If a dove meets a hawk, he will back off and get nothing, 0. If a dove meets a dove, both share the resource and get V2. The actual payoff, however, depends on the probability of meeting a hawk or dove, which in turn is a representation of the percentage of hawks and doves in the population when a particular contest takes place. But that population makeup in turn is determined by the results of all of the previous contests before the present contest. It is a continuous, iterative process where the resultant population of the previous contest becomes the input population to the next contest. If the cost of losing C is greater than the value of winning V, the mathematics ends in an S, an evolutionarily stable strategy situation having a mix of the two strategies where the population of hawks is V, C. The population will progress back to this equilibrium point if any new hawks or doves make a temporary perturbation in the population. The solution of the hawk-dove game explains why most animal contests involve only ritual fighting behaviors in contests rather than outright battles. The result does not at all depend on good of the species behaviors as suggested by Lorenz, but solely on the implication of actions of selfish genes. The War of Attrition Game. In the hawk-dove game, the resource is shareable, which gives payoffs to both doves meeting in a pairwise contest. In the case where the resource is not shareable but an alternative resource might be available by backing off and trying elsewhere, pure hawk or dove strategies become less effective. If an unshareable resource is combined with a high cost of losing a contest, both hawk and dove payoffs are then further diminished. A safer strategy of lower cost display, bluffing and waiting to win, then becomes viable, a bluffer strategy. The game then becomes one of accumulating costs, either the costs of displaying or costs of prolonged unresolved engagement. It's effectively an auction. The winner is the contestant who will swallow the greater cost while the loser gets, for all his pains, the same cost as the winner but no resource. The resulting evolutionary game theory mathematics leads to an optimal strategy of timed bluffing. This is because in the war of attrition any strategy that is unwavering and predictable is unstable in the sense that such a strategy will ultimately be displaced by a mutant strategy which will simply rely on the fact that it can best the existing predictable strategy just by investing just an extra small delta of waiting resource to ensure that it wins. Therefore only a random unpredictable strategy can maintain itself in a population of bluffers. The contestants in effect choose an acceptable cost to be incurred related to the value of the resource being sought, randomly selected at contest start, effectively making a related random bid, which becomes part of a mixed strategy. This implements a distribution of bids for a resource of specific value V, where the particular bid made for any specific contest is chosen at random from within that distribution. The distribution can be computed by invoking the Bishop-Canning's theorem, which holds true for any case of mixed strategy S. The distribution function in these contests was thus determined by Parker and Thompson to be This leads to the result where the cumulative population of quitters of the contest versus for any particular cost m in this mixed strategy solution is, which is shown in the adjacent graph. The intuitive sense that greater values of resource sought leads to greater waiting times is borne out here. This is exactly what is observed in nature for contests in a number of species, for example between male dungflies contesting for mating sites. The timing of disengagement in these contests follows the exact mathematical curve derived from the evolutionary theory mathematics. Asymmetries that allow new strategies in the war of attrition. There must be nothing that signals the size of a bid to an opponent. Otherwise this can act as a cue which can be utilized by an opponent for an effective counter-strategy for a mutant. There is, however, a mutant strategy which can better than that of a bluffer in the war of attrition game if such an asymmetry exists. This mutant strategy is the bourgeois strategy. Bourgeois uses an asymmetry of some sort to break the deadlock. In nature, one such asymmetry is possession, which contestant has the prior possession of the resource. The strategy is to play a hawk if in possession of the resource but to display then retreat if not in possession. This strategy requires greater cognitive capability than hawk, but bourgeois is still a very prevalent strategy in many animal contests. Some examples being mantis, shrimp and speckled wood butterfly contests. However, studies done on contests between speckled wood butterflies have been criticized for the methods used. Butterflies that were initially resource owners were held away from their territories very briefly in nets, a method that is suggested to tax the owner's metabolisms and potentially cause them to lose ensuing contests. Thus, evolutionary game theory explains a very wide range of rather mystifying behaviors in animals and in plant contests for many species with an illuminating clarity. Strategic alternatives in social behavior. Games like Hawk, Dove and War of Attrition represent pure competition between individuals and have no attendant social element to the game. Where social influences apply, there are four possible alternatives for strategic interaction that exist for the competitors. This is shown on the adjacent figure, where a plus sign represents a benefit and a minus sign represents a cost. In a cooperative or mutualistic relationship, both donor and recipient are almost indistinguishable, as both gain a benefit in the game by cooperating, i.e., the pair are in a game-wise situation where both can gain by executing a certain strategy, or alternatively both must act in concert because of some encompassing constraints that effectively puts them in the same boat. In an altruistic relationship, the donor, at a cost to himself, provides a benefit to the recipient. In the general case, the recipient will have a can relationship to the donor and the donation is one-way. Behaviors where benefits are donated alternatively at a cost are often called altruistic. But on analysis, such altruism can be seen to arise from optimized, selfish strategies. Spite is essentially a reversed form of altruism where an ally is aided by damaging the ally's competitor. The general case is that the ally is kin-related and the benefit is an easier competitive environment for the ally. Note: George Price, one of the early mathematical modelers of both altruism and spite, found this equivalence particularly disturbing at an emotional level. Selfishness is the base criteria of all strategic choice from a game theory perspective. Strategies not aimed at self-survival and self-replication are not long for any game. Critically, however, this situation is impacted by the fact that competition is taking place on multiple levels, i.e., at a genetic, an individual and a group level. The rationale and the mathematics that lie behind adopting one of these alternative social strategies will be covered in the following sections of this article.